Alright, class, so today we will be doing the Laplace transform of this function that I am in the process of writing down right now. So this is the problem that we're going to be taking the Laplace of. Now we have some initial conditions, which I'm going to write right here. Alright, so now we're just going to go ahead and start off by taking the Laplace of this function that we have right here. Alright, so I just took a little Laplace of the function, and we got that. So now we're just going to go through the process of trying to solve for y of s. So we're just going to go ahead and just simplify the equations that we have and everything in order to get what we need. Alright, so now you can go ahead and just do your the algebra to solve for this. So I'm just going to write the simplified version of the top.
Sort of.
Alright, now we're going to go ahead and do our decomposition, partial fraction decomposition, so that we can go ahead and just do the inverse Laplace of this to get it back into the t domain. Alright, just made a new slide. So now we're just going to go ahead and do our decomposition over here.
Well, that's just
velocity too. Take down velocity. Velocity. That's very complicated. Yeah, yeah. This is a perfect. Which whole system would be that? Do it per fan. It only matters how long it's going for.
Alright, so now we're just going to go ahead and simplify that. Oh, let me go ahead and just, this equation is still on the left side of the equal sign. This equation right here, okay, so that equation is still over there. Then we're just going to
you should divide that by 22. Like I did in my other calculation, but not the full out
But how come we're doing 8,000 and are we gonna show like the difference in the range? Cause the maximum is gonna be 1,200, right?
Take 12,000 and change for that, at least one.
So we can choose?
Yeah. That's why we were like, okay, we'll do 440. We're running doing fine with 1,000. I guess the trouble is figuring out which variables will change. So far, I've figured out that
Alright, so now we're just going to write the stuff to solve for our variables. So a plus c equals -1 because there's a negative in front of the s cubed on the left hand side of the equation. So then negative 6a plus b plus d. Oh,
the velocity is dependent on
equals 2.
Well, which everything like numbers,
I just chose the foot for that one.
and that gives you this.
No. This right here is 6 inches height.
Okay.
One foot, it gives you 4. It gives you 4.
15b.
That's equivalent to 2 inches of water, which is in the range of 25 to 30, which is good.
Alright, so now we can just do our algebra, like using two equations, setting them equal to each other and stuff like that to solve for our variables, for which I got a equals 1 over 10, b equals 1 over 10, c equals a negative 11 over 10, and d equals 5 halves. Okay? Now, from here we get to do, we're just going to go ahead and write that out, okay? Because now we have this. Now, what I did is I went ahead and I just took a 1/10 out of the whole equation just because we had a lot of 1/10s. And the reason why you want to take a 1/10 out is because it'll make it easier to recognize our Laplace transform function equations and stuff. It'll make it easier to relate it back to the tables that they have in the Laplace transforms. So that's the main reason why we wanted to go ahead and take out that 1/10.
And you scan.
If I have a scanner and a computer, then we're building a site. I could take pictures. I'll get back to you tomorrow. I have a scanner in my apartment, so I can scan it there and give it back to you tomorrow. You can go down and collect it. And then I'll also scan it into the drive.
That means I'm not going to work on it.
Alright, so now the reason why I did this 3 over 3 is because that's a Laplace transfer table thing to where this is sine, and if you recall, sine, the Laplace transfer form of sine is a over s squared plus a squared. So a essentially equals 3 because 3 squared equals 9. So that's the reason why we had to do that 3 over 3, because we have to get a 3 on the top of our fraction in order to make that Laplace transform true. right, so now we're just going to go ahead and do the Laplace transform now. So you have your differential equation table with the Laplace transforms in it. This is what you'll get as your final answer.
It's pretty much syrup. I just wanted to know what's food on, because then I can start
All right, and that's what our final answer ends up being. Is this right here. All right, well, I hope this video has helped you a little bit on taking the Laplace transforms. Okay, I'm just going to go ahead and point out something real quick before I close out, which is this part right here. And the reason why I did this is, once again, we had to get this as our transform function. So you'll see mainly the main reason why I did it was to get to this step right here. And the reason why this is valid is because this essentially equals S, right? So that means, because it's right here, right? So this means that this equals S. And as we recall, for our Laplace table, S squared plus A equals sine, right? So that's the main reason why we had to do this step right here in order to get that sine. All right, well, I just thought that I would point that out because it really, it's kind of tricky, and you can often miss steps like that when doing your Laplace, when knowing when to do that and stuff. So I hope me pointing that out has helped you out. All right, well, I'll see you next time then.